Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon, good evening to all the students and all the people who are taking this course. I am Raghunandan Sengupta from the IME department, IIT Kanpur, and this is the fourth lecture for the TQM 2. And as you know that it will be more of a building block for the design of experience, which we will cover within another 2 to 3 lectures. So, you are discussing about normal distribution. The relevance of normal distribution will come out later. We did mention that how if x is normally distributed with mean, mu and sigma square as the variance, how it can be transformed into a z distribution which is the standard normal, and how the tables of standard normal can be utilized to do the calculations. And we also initially, before that, we understood the concept of PDF, CDF, and that CDF would be utilized time and again in the calculations. We will see to that in due course of time. So, the standard normal distributions, basically if you consider the mean value, mode value or the median is 0 and as per the transformation, and the standard deviation of the variance is 1. So, if you go, if you are looking the distribution from your side, if you go plus 1 sigma on to the right, plus and minus 1 sigma on to the left, the overall coverage of the area you can find it from the standard normal table, and the overall area covered would be about, I am giving approximate values, it will be about 67%. And those points where if you go sigma plus and sigma minus, that means from the mean value, those are the inflection points, which means that the rate of change of the derivative basically takes place from negative to positive, positive to negative, and we know point of inflections are the points where the second derivative is also 0. So, in maximization and minimization, we know that the first derivatives are 0 and the second derivatives are respectively positive, and so on and so forth, based on which we can find out these values. So, consider in an examination 20% of the students failed, scored 40% marks less, 10% of the students obtained a grade 70 and more. And so, there are two sets of information. From these two sets of information, we need to find out the mean and the variance, which means two unknowns, two equations, and we can solve them as shown. They are very simple concept, they would not be utilized that much in TQM2, but I want you to go a little bit fast, so you will understand the significance of standard normal table. From there, we can find out Z1 and Z2 and mu and solve the problems accordingly. So, this is the same problem. If Professor Rampal's mathematics examination 20% of the students failed, obtained 40% marks and less, 10% obtained A grade, 70% marks and more, you can find out the mean and the standard deviation, which comes out to be 51.9 and 14.2. So, finding of the probabilities, as I said, I am just repeating, the first column consists of Z values, the topmost row consists of the decimal values of Z, and the in between values inside that matrix, whole matrix, is basically the CDF values. So, normal approximation to binomial distribution. So, consider x is binomial distributed with parameters p and n. P is the probability of success, q is the probability of the failure, such that q is equal to 1 minus p. So, if n, where if n is large and p is small, and then the distribution can be approximated by the normal distribution with the mean value as NP and the variance as NPQ, and you can convert that also into a standard normal table and do all your calculations. So, this is what is given here. But de Moivre's Laplace limit theorem, if you want to find out the probability of x being a random variable between a and b, and x is basically binomial distributed where n is very large, p is very small, and you convert to a normal distribution, then the values of the CDF values for till B and till A are given by the standard normal distribution. So, if how you convert the standard normal distribution is basically x minus mu divided by the standard deviation. So, here the standard deviation is basically square root of NPQ and the mean value is NP, and from that you can find out the values as given are like this. So, we have just highlighted. So, this is the first one is basically a CDF value starting from minus infinity to B. Second value is all the CDF values, sum of the CDF values from minus infinity to A, and difference between that will be given the total area covered from A to B. Now, if B tends to positive infinity, which means it basically the whole area becomes 1. So, obviously, the capital phi value would be 1. So, you have to find out the probability from A of x being greater than A. So, technically the value would be 1 minus the overall sum of the CDF values from PDF values. CDF value is the sum of that from minus infinity to A. So, 1 minus that will give you the whole area. So, let me again, I am sure everybody understanding that, but I am just highlight it. So, this is A. So, this is this value. So, 1 minus 1 is the whole area. So, 1 minus this will be give me this area. So, let me highlight it with another color. So, this is the value which I wanted. Now, if I want to find out as A tends to infinity minus infinity, so probability of x less than B. So, again the same distribution I will draw it. This is B. So, the area being given here. So, I need to find out the area here. This is basically this. So, I add up all from minus infinity to the value as given will be. So, you can find it accordingly, but obviously remember the whole area under the distribution, the whole area covered here is 1, whole area covered is 1, hence it can subtract from 1 or find out that integration of all these values. So, Markov's inequality. So, let Z be a non-negative random variable such that expected value of Z exists. So, it does not say anything about the variance, it does not say anything about type of distribution. Then for every positive t, we will have basically the probability of Z being greater than that fixed value of t is less than equal to, so that is the bound, is less than equal to the expected value of Z divided by t, and these inequalities are utilized for different cases. Now, let x be a random variable, which is the Chebyshev's inequality. Let x be a random variable such that the expected value, which is the first moment, and the variance, which is the second moment, exist. And then for every positive t, and it does not mention anything about whether it is a positive random variable or a positive negative random variable. Then the bound of the difference between x and its mean value would be greater than equal to some constant value into the standard deviation, which should always be less than equal to the 1 by square of that constant value. So, consider very simply that if t is 1, which is 1 plus minus sigma, so that would always be less than equal to 1, and you can find out the corresponding probabilities and the bounds accordingly. We will use them very rarely, but just as precursor. Now, in Bernoulli theorem, so let x n be the number of successes in n number of Bernoulli trials, each with success probability p. So, obviously, the unsuccessful one would be q. Then for any arbitrary positive epsilon, we will have limit of n tending to infinity, the difference between the relative frequency and the probability would be as close as possible to 0 as n increases. This is the basic essence. So, epsilon is basically a function of n, epsilon n becomes epsilon n or epsilon whatever you say becomes smaller and smaller as n increases. So, which means the difference between the relative frequency of the chance and the probability basically tends towards 0. So, this is what it actually means. Now, the central limit theorem. So, let x1 to xn be the independent and identically distributed IIDs, random variables each with expected value of xi's suffix i's being equal to mu suffix x, and the variances for each of them being sigma square suffix x. Then if we define S as the sum, so sum means that is basically sum of x1, x2, x3 till xn. And we defined this average of this sum as x bar n, then we will know that the expected value of S, which is the sum, is equal to n into mu x, because each expected value, they are independent IIDs. So, each expected value is mu x. So, how many of such mu x's are there? There are n. So, if you add them up, it becomes n mu x, and if I want to find out the variances of that, it will be basically trying to find out. So, as their IIDs, obviously the concept of covariances would not come. So, you will basically have n number of variances. So, n number of variances would be basically you would find out the variances accordingly. So, these are given and you can find it out as n sigma square. And for large n, as it becomes large n, so x n x bar n basically would have, what I mean is actually this. So, let me use a colored one. This is normal with mu x sigma square x by n. So, when you convert this, you utilize this and you get the concept of the standard normal. So, this basically this is the standard normal. And in case when, say for example, x is distributed or normal mu x sigma square x, then in that case z is standard normal with this. So, the only differences which is happening, which I should highlight, is this one and this one. In one case it is divided by square root of n, another case not, because you will understand the calculations would give you accordingly. So, we will consider sampling. So, there is point estimation, interval estimation, hypothesis testing. So, we will go slowly through point estimation, interval estimation, hypothesis testing. So, consider in sampling, you pick up a population, you have actual population of capital N, the population distribution is known, you have a parameter theta, theta can be scalar or vector depending on the problem, and you have basically pick up a sample, sample is of size n and the sample distribution is given. So, you want to basically find out, in some cases the sample distribution will be given and in some cases the sample distribution has been found out. So, if you would ask that what is the sample distribution you want to find out, that it can be either related to the parameter which you are trying to find out from the sample distribution, or it can be, say for example, the random variable which basically denotes the sample distribution. So, in case if x is the random variable, then from the sample you get the simple sample mean. So, if a distribution of this is known, our main task would be to find out the distribution of x n bar, or else it can be I want to find out, say for example, x sum star whatever it is. So, x star would basically be the minimum values between x 1 to x n. I want to find out the distribution of that. So, that is also important. So, that may be the sample distribution which I am looking for. So, in the continuing this example, consider a population having the elements 1, 3, 6, 7 and here n is 4, and the mu value would be basically the sum of all these 4 elements. 7 plus 6 is 13, 14, 1, you add 1 and plus 3 17, 17 by 4 is the population. If we take n is equal to 2, that means we take 2 observations at each go, and then the 2 observations can be any combination. It can be 1 1, it can be 1 3, 1 6, 1 7, and the other extreme it can be 7 1, 7 3, 7 6, 7 7. So, then the possible values of the sample average can be 1 plus 1 divided by 2, which is 1, and another extreme is basically 7 plus 7 divided by 2, which is 7. So, this would be the sample statistics for which we need to find out the distribution function. Now, simple random sampling can be with replacement and without replacement. So, with replacement means that you pick up one observation and you do the checking. find out what is the observation, and then you continue doing the random sampling with replacement. So, you pick up, check, put it, pick up, check, put it, and without replacement is basically pick up, find it out find out what is the probability, and then remove that object, and then basically do the sampling or find out the probability again. But the problem is here. So, say for example, you have a big sample of size 100, there are chits marked 1 to 100, each being only happening once. So, if you do it with replacement, the probability corresponding to pick up any chit remains the same. So, if you pick up one, find its probability as 1 by 100, note it down as 1 by 100 and put it in the box. If you continue doing it, the probability always remains the 1 by 100. But in the other case, if you pick it up and basically remove it, so obviously it means the probability of picking up 1 the next time, if 1 has been picked up in the first time, basically becomes 0. Or say for example, the probability of picking up number 2, if number 2 has not been picked up in the first trial, it will be 1 by 91. So, obviously the probability will change, but it should be remembered. But if this actual population of the sample size is huge, then the corresponding differences in the probabilities does not change much, which would not be much of a difference in the actual answer. Note, if x has a distribution such that E of x is mu x and variance of x is sigma square, then the expected value of xi and variance of xi continue to remain as mu suffix x and sigma square suffix x. Now, there are different types of sampling. So, they can be probability sampling, under which you can have simple random sampling, stratified sampling, cluster sampling, multi-stage sampling, systematic sampling. Under judgmental sampling, you have quota sampling, purposeful sampling, and all these things. Consider the chi-square distribution. So, if you have a basically chi-square distribution, how it is formed. So, consider you have n number of z distributions. Z is basically the normal distribution. So, consider there are boxes, each are z distributed, and these boxes has infinite number of observations. So, if you pick up one observation, that would be the z distribution. You pick up each observation, square them, add them up, and the value which you get, you keep aside. You do the second time, pick up the second observation from box 1, second observation box 2, nth observation box n, square each of them individually, add them up and write down the values. So, if you continue doing it, the values which you have, the square sum of the squared values, if you plot them, then the distribution basically is chi-square. So, this is what we mean by chi-square distribution. So, which coming back to this, suppose z1 to zn are n independent observations from normal 0 1, then z1 square. So, 1 means basically the suffix, z2 square, the 2 basically means the suffix, till zn square are chi-square distributed with degrees of freedom n. So, this is the distribution of chi-square, and the n, if n is the parameter which is the degrees of freedom. So, the expected value is given by n and the variance is given by 2n, and the chi-square distribution looks like as given here. So, depending on the degrees of freedom, whether 1 or 2 or 5 or 10, the distribution would basically take the shape as given. So, along the x axis you have the chi-square values. So, those are now the PDFs, and along the y axis you have the PDFs corresponding to the chi-square. Now, you have the t distribution. So, how do you form the distribution? Consider that the y is already chi-square in n degrees of freedom. You have another distribution which is z, which is standard normal. Then, if you find out the ratio of z divided by the square root of chi-square by its degree of freedom, you will have basically the t distribution. So, that will give you one thing should be remembered, that t distribution is almost symmetric to the normal distribution. So, if you increase the degree or the degrees of freedom or the n value, then t distribution becomes exactly equal to the normal distribution in the sample size increases. So, t distribution PDF is given by this, expected value is 0, because t distribution, as I said, is looks exactly symmetric to the z distribution, and the variance is given by n minus 2. So, you can find out, and obviously it would mean, it is very interestingly, as n increases, the ratio becomes 1, which is the variance of the standard deviation of the standard normal distribution. So, if you look at this set of values or pictures for degrees of freedom of 1, 10, 20 and 30, the PDF of the t distribution is drawn. Along the y axis you have the PDF, along the x axis you have the t values, and if you plot them, it becomes almost exactly equal to the normal distribution as the degrees of freedom increase. The F distribution is basically a combination of 2 chi-square. So, consider x is chi-square with degrees of freedom of n, and y is chi-square with degrees of freedom m. So, if we find out the ratio of chi-square divided by its degrees of freedom n, and that is divided by chi-square with divided by degrees of freedom which is m, then that ratio is known as F distribution with degrees of freedom n comma m. If you reverse the ratio, that means y by m divided by x by n will give you basically the F distribution with degrees of freedom m comma n. So, the F distribution's PDF value is given, where nm and nm are the parameters. Expected value is m divided by m minus 2 or m divided by n minus 2 depending on which ratios you are taking, and the variance would be given as it is given, where if it is n by m or m by n, the values would be taken accordingly, whether n or m you can decide it accordingly depending on the ratio. The F distribution is also not symmetric like I-square. So, depending on the degrees of freedom of 1 because now there are 2 degrees of freedom m and n, depending on 1 or 1 10 10 1 and 10 10 10, the distribution would be given as shown in front of you. So, some interesting results are, if x1 and x2 till xn are n observations from the normal mu suffix x and sigma square, and the sum which is x1 till xn divided by n is basically given by x bar, then obviously we will know, which we have discussed in details just before just at the beginning of few slides of this lecture, that this value is the Z distribution. So, this is a distribution because Z is normal 0 1, and this x bar n normal mu sigma square n, and based on that you are getting this standard normal. In case x is normal with mu sigma square, then obviously it will be x minus mu by sigma, that is distributed in 0 1, and you do your calculations accordingly. So, some interesting results are, consider you have a sample and you want to find out the sample standard deviation, which is also known as standard error, or you want to find out the sample variance. So, sample variance can be found out in 2 different instances. Number 1, when the population mean is known, and one case is when the population mean is not known. So, when the population mean is given, then obviously the standard error whole square, which is the variance of the sample, is given by 1 by n summation of xi minus mu whole square, that summed up. But if you are you do not have any information of the population mean, so what you do is that you would use that sample set of observations for the first time and find out the sample mean. So, mu is replaced by x bar n. So, the moment you use that for the first time, you lose 1 degrees of freedom, hence it is divided by 1 minus divided by n minus 1 as highlighted. So, I will try to highlight it with different colors. So, what is important to note down? I will just highlight it once again for the benefit of the student. So, this is what is, this part is important along with this, and another part which is important is this along with this. So, so this gets replaced here, and as you utilize this, you lose 1 degree of freedom here. Now, if you come back, use these concepts and also remember these. So, utilizing these 2 concepts, this one for the mean and this one for the standard error, you will find out the following results, which are as follows. the ratio of the square of the standard error or the sample variance divided by the population variance multiplied by the n factor would give you a chi-square with n degrees of freedom. So, remember this, I will again highlighted few things with yellow color. So, if it is dash, this is n, this is n. In the other case, if it is without the dash, this is n minus 1, this is n minus 1. So, this would make things clear to you where the changes are, and they are very logical. Obviously, the proof is not very intense, it can be proved, but it is not actually necessary for this TQM course. So, this will give you the chi-square with n degrees of freedom, chi-square with n minus 1 degrees of freedom, and in the other case when you have when you want to find out the distribution corresponding to t n minus 1. So, obviously, in that case that sigma square, which is the population variance, is being replaced by the standard error of the sample, and as you replace the standard error in the sample, you will get the t distribution with n minus 1 degrees of freedom. So, okay. So, let me again say why I did say, but I did not highlight. So, I use another color or red one, yeah. So, this is being replaced in place of sigma square. So, and obviously, this becomes, I am not going to highlight this remains square root of n because it is coming down. So, in this case it is t n minus 1 t distribution, and if you compare this, so this was what, in that case it would have been x n . So, the changes where they are occurring, I will just use another color. So, this and this are important to note, and this and this are other important things to note. So, if x1 to xn are and are m x observations from distribution normal with mu and sigma square as the mean and variance, and y1 to im are another normal distribution with mu and sigma square with this corresponding suffix, then you can find out that the ratios of the corresponding distributions would be f distribution. But there are two important points I want to mention. Number 1, in case these are x s without the suffix, then in this case the f distribution loses 1 degrees of freedom both for m and n. In case the ratios of f s dashes in place of s, so these are there. So, in that case it will be f distribution of m and n. So, with this I will close this 4th lecture and continue discussing in the 5th lecture correspondingly the other concepts of inference techniques. Have a nice day. Thank you very much.